We're going to spend this stream going through the exercises for section 5 of my upcoming PyTorch course. By the time you watch this, the course may already be out. Essentially, going modular is we've been working through a lot of notebooks so far. So where we'll be up to in the course by the time you watch or do these exercises, we will have just gone through section 04, which is PyTorch custom datasets. The notebook for that is here. If you go through all of this, you learn how to load your own custom data set and then build a PyTorch computer vision model to fit that data set. And by the way, if you're tuning in live and you're in the chat, please just let me know if the audio is okay. Pretty sure it is. But what the whole essence of going modular is rather than starting every notebook and writing all of this code over and over again. So we've got some functionality here. We build a model right down here, I believe. Maybe we search for our model, tinyVGG. Yeah, so we've built this model. We've built a data loading pipeline. Here's the model class. Rather than rewrite this all the time, you might come across some PyTorch repos that have different Python scripts. So that's what going modular is so we go from a notebook code, like Google Colab, and we want to turn all of our most useful code cells into Python scripts like this. So I'll give you an example. If we go PyTorch do this for their latest state-of-the-art computer vision model. So this is a blog post here on the PyTorch blog. How to train state-of-the-art models using PyTorch's or Torch Vision's latest primitives. So if we go down here, there's a training script somewhere here, training reference script. And you'll see this across many different PyTorch repos. Yeah, so references to build a classification model, specifically the models that get state-of-the-art results in Torch Vision on ImageNet. They break it down or break the training code down into a series of Python files. So train.py, transforms.py, utils.py. Then you can pass a bunch of hyperparameters to those Python scripts. And then to train a model, you call something like this. So if we look for train.py, yeah, torch run is just another PyTorch library for running a training script in a specific way. So this here distributes the training script across, it looks like 8 GPUs. So then you've got a model type, you can use different weights and yada, yada, yada. So this is what we want to end up with. That's the whole premise of going modular, is we want to take our existing working notebook code, something like this, and we want to break it down into a series of Python scripts like what we've got. And then eventually we want to get to the stage where we can call, say, a line like this, python train.py with a model, a batch size, a learning rate, a number of epochs. So that's what section 5 of the PyTorch course goes through, is take our notebook code and get it into Python scripts. And so this is my workflow that I actually use day to day as a machine learning engineer. I start in, can I view this as full screen? Maybe not. Maybe I can just zoom in. There we go. I think this will be a good thumbnail, won't it? I start in Jupyter/Google Colab, and I do a whole bunch of experimentation in these because it's quite easy to do. It's very visual. And then once I've got something working, I move my code into Python scripts so that I don't have to rewrite the same code over and over again. So this, for example, is datasetup.py. Ashik, what's going on? Can you hear me all good in the chat? My camera's busted. I need to fix up. I messed up the cable. I moved places and the cable connecting my camera. So it's just audio and screen today, but that's all right. Here's what we're trying to do. We're going from a notebook like this to a series of Python scripts like this. And again, we're just doing the exercises that are part of this section. Let me just zoom out, if I could. My goodness, I'm stuck. There we go. Okay. So this is how you'll often find PyTorch code in the wild. And so you'll have been through all of these materials here. You can find these all on Learn PyTorch.io, by the way, and the PyTorch deep learning repo. But this is the purpose of this stream, is to go through the exercises for number 5. So that's what we're up to. TK means that I have to come and check it later, but we've got some exercises here to run. The first one, turn the code to get the data from section 1, get data above, into a Python script. Now, I've already turned this into a template PyTorch, a template Google Colab notebook under exercises/solutions. By the end of this stream, we want to fill out these code cells. We want to complete these exercises. So I'm doing this live so that you can see how I work through these problems. And by the way, I'm just going to copy this to my Google Drive so that I can work on it, save it back to GitHub and whatnot. The code that we write in this stream is only one version of the solutions. So there are probably a few different ways that we could do this, but I'm just going to show you one example. So turn the data from section 1, get data, into a Python script such as getData.py. And now for context of that, you will have already gone through, if we go back here, there's a notebook that is going to create a lot of these scripts for us. So part 2, scripts mode. I'll just show you how it works. And by the way, thanks Ben Isle for going through the notebook and checking out the typos and make sure the code works. So let's open this in Colab and just run it end to end and see what happens. Okay, here we go. You ready? We're just going to run all of these cells. So there's a Jupyter magic called write file that starts with 2 percentage signs. And what this is going to do is essentially going to write all of the code from this cell into a file called hello-world.py. So if we ran this particular code cell, it would save this as a Python file called hello-world.py. And then if we ran Python hello-world.py, we would get this output, hello world, machine learning is fun. That's this here. So I've just run this script and have a look at what we get over on the side here. We get a folder called data. We get some pizza, steak, sushi images. We've got a training and test folder. Now this is in standard image classification format. So the sushi images are in here. We covered this in the last section. But now we've got a going modular file. And you'll notice here that we've got datasetup.py, engine.py, modelbuilder.py, train.py, utils.py. And that is what this notebook creates. So under every section, we've got some functionality. Create datasets and data loaders. This is the get data section. This is what we're trying to answer for question 1. Turn the code to get the data from section 1, get data, into a Python script such as getData.py. So we want to somehow, let me just tidy this up. We've got a fair bit of stuff going on here. I might put this right over here, get rid of that, and get rid of that, and get rid of that. Beautiful. So we want to turn this section into a Python script. So we've done that for down here. So create datasets and data loaders. We have some functionality here from the previous notebook, which is number 4. So the code in 05 is the code from 04. It's just been reduced to only the most significant parts. And so if we have some functionality here, create datasets and data loaders, and then if we decide, yep, that's good, well, we can turn that into a Python script. So 2.1, create datasets and data loaders. We have write file going modular / datasetup.py. Now this is a magic Jupyter code. You can tell it's magic because of the percentage here. And then if you want to find out magic Jupyter codes, Jupyter commands, you could go like this. Beautiful. And there's a whole documentation on what they do. I'll let you read into that. However, what this is going to do is going to write all of the code in this cell to a file called datasetup.py. Now, do you recall the whole goal of going modular is, where were we? There's one bold line here. The main concept of the whole section is to turn useful notebook code cells into reusable Python files. And so that's what we're doing here. We've decided that our dataset and data loader functionality is working. So we turn it into a function and we write it to file. So if I write this cell here, run this cell, sorry, it's going to overwrite the file here. Then if we have a look over to going modular, we've got datasetup.py, and if we open that up, you'll notice that we have the exact same code on the right. This is datasetup.py as what's in this code cell here. So that's what that magic function has done for us. This magic function has taken all of the code in this cell because we've deemed that code to go, you know what, this is useful code. I want to keep using that. I don't want to have to rewrite this all the time. We've now saved that to a script called datasetup.py. So we could use this script to create our data loaders. Now, this is where exercise number 1 comes in. We want to turn the code to get the data from section 1, get data, into a Python script such as getData.py. Now, the ideal setup here would be that we can call, now this is from a Colab notebook, by the way. It might be different if you're using the command line. We want to run getData.py, and if we run that, it's going to error because getData.py doesn't exist in this notebook. We want this to download the data in the same format that we have in notebook number 5. So what we can do is we've already got the code to download the data. What we can do is we can take that code and turn it into a Python script. Let's see how we might do that. We'll come back up. This is section 1, get data. So we want this to be a Python script. So let's copy this code here from Going Modular script mode. And we're going to come into Going Modular exercise solutions. And I'm going to copy this code into here. So if I run this cell on its own, because we now have code to download some data and we've run it, we look over here, we have a folder called data, we have pizza, steak, sushi, test, train. Now you can step through this code. Essentially all it's doing is making a call to GitHub, downloading a zip file from GitHub and unzipping that code there. However, how could we turn this into a script called getData.py? Well, if we go back here, what did we use to create our datasetup.py script? We used write file going modular / datasetup.py. Well, how about we try that out? Something similar here. This is how beautiful Jupyter Magics are. Now, you don't have to create Python scripts like this. I just find it helpful to create a script like this when I'm coding in a Google Colab notebook or Jupyter notebook, because I tend to do a lot of my experimentation in a notebook. And then if I find some useful code, well, hey, I can turn it into a Python script just like this. So what do you think will happen now if I run this cell? Let's try. Oh, we've got writing datasetup.py. So we refresh. Look what we have over here. Datasetup.py. Now if we come over there, that's how simple it is to turn a useful code cell. That's what our whole goal is here, right, of Going Modular. Take our most useful code and put it into Python scripts so that we can reuse it over and over again. So there we go. Now, if we run this datasetup.py, what do you think it's going to do? Well, it's going to run all of the code here, of course. Well, let's try it out, hey? So, but previously, we tried to run this command and it said Python 3 can't open file get data.py. Now, I just want to exemplify how this is going to work. So to do so, I'm going to delete this folder. Oh, we might need to delete this on the command line. So remove rf. Be careful when you use this. Data. Is that going to remove the directory? Beautiful. So if we refresh, we have no data file over here. This comes with Google Colab. So sample data, I think we can just ignore that too. We can just rf sample data. I didn't create that. That just comes standard with Google Colab. Beautiful. So I'm just taking a sip of water. It's a beautiful rainy day outside, but it looks like the sun is popping out. Where were we? So we write the file to datasetup.py. Now, we've got datasetup.py, and if we wanted to run that within a Colab notebook, we can call python getData.py. If we wanted to run it in terminal, this is in the PyTorch Deep Learning course repo on my MacBook. I'm just going to exemplify this. Python getData.py. We don't need that exclamation mark at the start if we're running it in a command line, just like that. We can just run it like this, Python getData.py. But it's not going to work because I don't have this file in my PyTorch Deep Learning folder. But let's see what happens if we run it here. Can't open file getData.py. Oh, excuse me. We've called it the wrong thing. Did you catch that? I want it to be getData.py. So I'm going to delete this. GetData.py. That makes a lot more sense because that's what we said here, getData.py. We run that, so it's going to write get data.py. We've got a Python script over there, which is just all of the code that's in this cell. And then we run that. Did not find data, so what this is going to do is going to check to see if the image directory exists, aka the data folder. And if it does already exist, it's not going to re-download it. So it's downloading pizza, steak, sushi data, unzipping it as well. Refresh, data, we get pizza, steak, sushi. Beautiful, look at that. That's how quick we can turn some useful code into a Python script. And now, if you were to do this over and over again with your useful code, you might end up with something like this. And this is what we've covered in the video of going modular. But that's how we created all of these. So I believe that's exercise 1 done. Now, if we run this again, is it going to catch the fact that it exists? There we go. Data pizza sushi directory exists. Oh, it still downloads it. So maybe that's a little extension to go, if it already finds that the directory exists, it doesn't re-download the data. So there we go. Pizza, steak, sushi, test, train. All right. Now, let's keep going. We're up to exercise number 2. Use Python's Argparse module to be able to send the train.py custom hyperparameters for training procedures. So in the previous notebook, we finished off with so this is going modular script mode. We finished off with a training file that allows us to train a model. So if we go into train.py, this allows us to train a whole PyTorch model by importing various other scripts that we've run. So import data setup, import engine, import model builder, import utils, and this is train.py itself. So what we want to be able to do here is I'll just show you what we're working towards. So if we go Python train.py, and then we say we wanted to train a model, tiny VGG. We might not need the model one though. What's a better example? Let's say batch size, we wanted to use 64. Let's say a learning rate, we wanted to, you can see in the code cell above, in the text cell, that there's an example here. Let's say we wanted to use the learning rate 0.001. And let's say we wanted to train for 25 epochs. So how might we influence our train.py script to be able to accept arguments like this? And you're going to see this quite often when you come across PyTorch scripts and Python scripts in the wild, just in general. This is not PyTorch specific, by the way. This is Python script. You'll find this in many different Python programs, but it's typically, you'll also see it with PyTorch. So just like we've got our getData.py script, we want to alter our train.py script from in here. Train.py, if you run this notebook end to end, train.py will be generated. We want to alter it in some way that it can take argument flags. So argument flags are what we just looked at. Learning rate. These are called argument flags. Or maybe there's a better name for them. If you have one, please let me know. Otherwise, I just call them argument flags. So let's get our train.py script. And I'm going to bring that in here. Going modular. Wonderful. So this is our train.py script. And you know what I just realized? We might need every other script in here because this is what... Oh, I'm about to sneeze. You can't see this, but I'm about to... So our train.py script, because it leverages other scripts here, we may need to bring those in as well. So how could we do this? What if we get rid of that? I wonder if we could just copy this particular file, going modular. We could just copy all of these. Data setup.py. Yeah, that's a good idea. So let's just get all of these in here. So what I'm going to do, I'm going to bring this code in here into Google Colab. This is because train.py leverages all of these other ones here. So we need them. So let's go code. Let's create data setup.py. And this is good practice, by the way. We don't have to do this way. You could just write a script some Python code to download this file off GitHub because it's public. But I'm just going to copy them all in here manually just to do things inefficiently and show you what it looks like to create a series of Python scripts. So then we'll do engine.py. So I'll just run this. This is going to create datasetup.py. And if we have a look at that, so datasetup.py. Now let's do the same for engine.py. That's going to create engine.py. Beautiful. Now all we're doing is we're just replicating the structure of going modular so that we have access to all the files that train.py has. So this is the going modular file. We're going to do model builder. So that way, if we alter train.py to accept argument flags, we still have access to all of the other scripts. Otherwise, we'll get errors. Write file, model builder, .py. And then what are we missing? I think there's one more, utils, because we've already got train.py. Utils, short for utilities. So then we'll come in here and we're going to write this utils.py. Now, you see, this is a good example of creating a series of PyTorch or Python scripts of PyTorch code. I get Python and PyTorch mixed up because there's a lot of pies. But what we've done here is if we had a notebook previously that had a lot of useful Jupyter Notebook cells or Colab cells, like this is a useful function here. All we've done is we've written a single line at the top of that cell to say, hey, save this to file. And so that we can leverage this later on. And so if we did want to leverage these later on, we could save it to a file on GitHub like we've got here, going modular. And then we could just download this file or clone this repo and then access this code over and over again. So that's the helpful functionality of turning your useful notebook cells into Python scripts. So now if we write train.py, and if we try to run this, it's going to error because we don't have access to command line arguments. Oh, I didn't know this. Apparently it works. That's news to me. But I don't think it actually uses this functionality because see how we've set batch size? I'll show you how we can do this. So see, now we have a whole bunch of different Python scripts here on the left. And we want to alter this train.py script to use a library called, I believe up here where we've got the question, we want to use a library called Argparse or a module from Python. Use Python's Argparse module. So Python Argparse. Here we go. So if we go import Argparse, I'm just going to, let me just go back here and then we want this one. So what we're going to do is we're going to leverage similar code here so that we can accept argument flags in our train.py script. Train.py. Let's now import Argparse. Argparse. Now we want to create a parser here. Create a parser. So parser. You can also call it args. Oh, sorry. We'll get to that in a sec. So let's go parser equals argparse. This is just straight out of the Python documentation. Dot argument parser. And we're going to go description equals get some hyperparameters. So that's what we want to do. And now we want one for get an arg for, let's change all of these into arguments, hey? Num epochs, get an arg for batch size, get an arg for hidden units, and get an arg for learning rate. Beautiful. So let's add some arguments to our parser. Add argument. And we want to call this, let's call this one num epochs. And then we want type, it's going to be int, and then help can be the number of epochs to train for. And then we're going to set the default, I'll set the default over here. Let's just train for 10 epochs by default. Beautiful. So let's now do batch size. Do you see what we're doing here? We're customizing our program to just pass it things on the command line with various flags here. So batch size, the default, what should our batch size default be? Let's go 32. And then the type here is going to be int. And then the default, the help can be number of samples per batch. Beautiful. Then we can go parser, add argument. Then we pass it in here. We want hidden units. So let's call this hidden units. So the default here can be 10. And the type is going to be int as well. And then the help is going to be number of hidden units in hidden layers. Now you could, as you probably noticed, you could create as many of these as you want for your Python scripts. Especially with deep learning models, you might have a lot of hyperparameters you want to tweak. So just keep in mind that you can create as many of these as you like. And in fact, that's probably a good challenge to set for yourself. Add argument. Let's go final one. Learning rate. The default, we'll set this to 0.001, and type is going to be float, and then help equals learning rate to use for model. Beautiful. F6 Ari, ask in the chat, are you actually building an app or learning this stuff for fun? Both. At the moment, this is part of the course that I'm teaching. The code that we're writing now is part of exercises for a course. But I, as of now, am working on Nutrify.app, which is a computer vision application for taking photos of food and learning about it. It uses machine learning. Basically turning food into QR codes. But now we've got arguments here for the 4 different things that we're after. We have an argument for number of epochs, batch size, hidden units, and learning rate. So now we have to get our arguments from the parser. And so this is where this line comes into play. So because we've set up a parser to pass different arguments, we've passed a lot. We've passed the command line, passed to our program. We need a way to retrieve them. So this is just setting them up. Now, this is going to retrieve them. So args, you'll often see the conventional name args, short for arguments. We're going to pass the args of our parser. Pass args. So that just means get our arguments from the parser. Now, if we wanted to set these variables here, we could go args dot. Now, this is the number of epochs. We want to get num epochs. So num epochs. Beautiful. And then if we wanted to set this, we could go args dot batch size. Now you see I'm getting this text here that comes after the double flag. And then if we wanted to set the hidden units, args dot hidden units. And then if we want to set the learning rate, args dot learning rate. Beautiful. So we might do a little print statement here to see if it works. Print info. So let's go training a model for num epochs with a batch size of using let's go hidden units and a learning rate of learning rate. I love print statements. Beautiful. So let's run this and see what happens. And we'll just delete this. What do we get? Oh, we got a typo. Add argument. Oh, an extra M. Argument. How does this go? Run it again. So there we go. We got the default. I'll just get that documentation out of the way. Our default parameters are being used. 10 epochs with a batch size 32 using 10 hidden units and a learning rate of 0.001. Now, do you notice that this is where it comes from the defaults? So we set the default for number of epochs to 10, the batch size to 32, the hidden units to 10, and the learning rate to that. So let's try change these values, not here, but in this line here. Python train.py. So let's set the number of epochs. Let's just do 3 epochs this time. Keep our experiments quick. Let's change the batch size to 64. And let's change the hidden units to, how many do you think? Let's do 64 hidden units as well. Why not? Make our model a little bit bigger. Hidden units, 64. And let's go learning rate. We'll use 0.002. See what happens. Oh, would you look at that? Training a model for 3 epochs with a batch size 64 using 64 hidden units and a learning rate of 0.002. So that is how we can use command line argument flags within our Python scripts. We can use Python's Argparse module, and then we can add our own arguments here. So this is very helpful for writing reproducible code. So if we wanted to use the train.py script over and over again, we could set it up so that it uses different kinds of arguments here for different types of experiments. And again, you can create unlimited different arguments here. So there was one more thing that I wanted to do in the exercise, and that was we want to be able to use a different training and testing directory. So what if we had different data setups? So right now we've hard-coded our training and test directories to use pizza, steak, sushi, test, and train. What if we wanted to change them? And by the way, do you notice how we're leveraging? Let me just show you how we're leveraging every other script in this. So in our train.py file, we are leveraging datasetup.py, we are leveraging engine.py, we are leveraging modelbuilder.py, and we are leveraging utils.py. And so if we come into here, if we want to create our data loaders, we run data setup, create data loaders. Now this function comes from within datasetup.py, create data loaders. And then if we have our model builder file, we build the tiny VGG model from that. So instead of writing all of this model code over again, we leverage it by just calling it. That is the power of turning your notebook cells into Python scripts. We create a loss function and an optimizer. You could again potentially turn this into an argument flag for using different losses and different optimizers. The same thing with our engine. So to train our model with our various hyperparameters, we leverage our engine.py script, and there's a train step function. There's a test step function, scrolling too fast, test step, and there's a train function here. So this is engine.train. So engine.train is going to run this function. So instead of us rewriting all of this, we save it to a script. And then we've got utils.save model. That's going to save our model to file under a directory called models. So let's now make one more argument flag, or two more, to specify the directories here. So traindir and testdir. We've done this before. So create an arg for training directory. So parser, what are we going to do? Add argument. And we can go flag traindir for training directory. Let's set the default equal to the current value because that's where our data lives. But with the argument flag, we could change this if we wanted to. The type is going to be string. And let's say the help can be directory file path to training data in standard image classification format. Ashik, you're right. You can now publish this as a package and use arguments to run experiments. Yep, that is another extension that you could do, is go how to publish a Python package. There we go. Great articles here. How to publish an open source Python package. So that is, you've now got Python files and they could be packaged up into something that you could pip install so that someone could leverage your code. So then we're just going to copy this. We're going to do the same thing for testing. Test directory. Let's change this, the default to be test, to testing data. So now, if we run this, let's just for fun change it up. This time we'll do 5 epochs with a batch size. Can we fit 128 samples in? And we'll do 128 hidden units, why not? And we'll do a learning rate of 0.003. Let's see what happens. Oh, I might put a little adjustment here. So traindir is going to be args.traindir. And then we're going to go args.testdir. And then I'm just going to put out another print statement here so we know what we're doing. Print info is training with training data file. We'll go here. Will be traindir. And then we'll go print info. We will go testing data file equals testdir. So let's run that. This is going to overwrite train.py and let's see if it worked. Beautiful. Look at that. So we've got number of epochs 5, batch size 128, using 128 hidden units and a learning rate of 0.003. And we're training on data/pizza steak sushi train, and we're testing on this test data. Of course, you could change these if you wanted to by going traindir, and then you could pass in some other dir here, and testdir, some other dir. Excuse me. Some other dir. But by default, it's going to use our existing files. So we're just going to leave that as that. I believe that is exercise 2 over. Training and testing directory, learning rate, batch size, number of epochs, number of hidden units. Beautiful. Okay, let's move on to the next one. Exercise 3. Do we have any questions if you're watching this in the chat? Otherwise, I'm going to move on to step number 3. Oh, and just remember, for train.py, because it leverages all of the other files here, we had to copy them into here, otherwise it won't work. So if your code uses code that's not available, what will happen? It will error. So let's create a Python script to predict /predict.py on a target image given a file path with a saved model. For example, you should be able to run the command python predict.py sum image.jpg and have a trained PyTorch model predict on the image and return its prediction. To see example code, check out the predicting on a custom image section in Notebook 4. You may also have to write code to load in a trained model. Okay, so let's create a function, predict on image. And what are we going to need? We're going to need an image, and we're going to need a model. I think that might be about it. And we might need to load a model. Def load model and file path in here, and then we can go return model. And maybe we don't actually need that. Model equals load model. And we'll go in here, file path, load model, and we'll pass in the file path. And then this is just pseudocode for now, by the way. Predict on image. Image equals image. Or pred equals model image. We might need to pre-process the image. Pre-process the image. So we're going to get this cell working in a Jupyter notebook or in the Colab notebook before we turn this into a script. So the end goal, this is what we're going to work towards. Python predict.py sum image.jpg. Can't open predict.py, no such file or directory. Okay, so if we look at our, this is again another tip, right? If you're trying to figure out how to write some code, look at code you've written before. And you might not have code you've written before, so then you can just Google it or search it. So this is what we've done. We're working on 0.5 at the moment. We've already been through 0.4, so section 11.3, let's use some code we've looked at before. So putting custom image prediction together, building a function. What did we do here? So let's put them all together in a function we can easily use over and over again. It takes in an image path, converts the right data type. Yes, that makes sense. Make sure the target pixel values are in the range 0 to 1. Transforms the target image if necessary. Make sure the model is on target device. Makes a prediction on the target image with a trained model. That's what we want to do. Converts the model's output logits to prediction probabilities. Converts the prediction probabilities to prediction labels. Plots the target image alongside the model prediction and prediction probability. Okay, we don't necessarily need to do all of these steps, but let's just have a look at what we did in our previous setup. So we loaded in the image. So target image equals torchvision.io, read image, string image path, and we turned it into type float32, and then we divided it by 255 to get it between 0 and 1. So let's get torchvision in here. Torchvision is packed with a bunch of different helper function code to help us pre-process images. So let's create function to load in the model, and then function to load in model plus predict on select image. And let's just pass in maybe an argument here. Some image.jpg. Well, let's keep going. We'll pre-process the image. We'll get Argparse here actually. Import Argparse. And we will go Argparse or parser equals Argparse dot argument parser, and then we'll go parser dot add argument, and we'll go image, and then we'll go help equals target image to predict on. And then we'll go args equals parser dot parse args, and then we'll go image path equals, this is just creating a parser. Get the image path, args dot image. And then we're going to go print info predicting on, and we're going to pass in image path. Now we're going to need a path to a trained model. So how about we do that? So get an image path. Now let's do the same for get a model path. Parser add argument, and we want model path help equals maybe target image path file path target model to use for prediction file path, and then we will go type equals string. Then the default can be, let's go, we'll copy this path. This is our saved model. So we'll go, the default is models 05 going modular script mode tiny VGG model. That is the model we just trained with this function up here. So at the end of this train.py script, we call save model, and it saves a model to models 05 going modular script mode tiny VGG.pth. That's saving a PyTorch model. So if we want to run predict.py, we need to load that model in. So that's our default model. Of course, we could change that if we wanted to. And now I believe because we are loading this model, we need to load in the model here, but we are also going to have to import modelbuilder.py because we saved the state dictionary up here. If you look into the save model function, which is in utils.py, because we used the save state dict, we need to recreate a model object and load in that state dict. Recall from a state dict of a model contains all of the parameters associated with that model, but to load in a state dictionary, you need to load it in to a model instance of the same type model. Let me show you. It looks a lot easier to understand that with code. So in here, if we import model builder, let's set up the model equals tiny VGG, and we need model builder dot tiny VGG. Now we need to set up a few things. Input shape equals this. We need the same number of hidden units as we used by default. So that's going to be 128 in our case. And then the output shape. Do we have a doc string here? No, we don't. But if we go into modelbuilder.py, we have input shape, hidden units, output shape. So they're the parameters we need to use. We need to use the same, just right here, need to use same hyperparameters as saved model. So output equals 3 for the number of classes. The input, recall, is the number of color channels. Hidden units is 128 because our saved model uses 128 hidden units. And we want to predict on the image, get the image path. We've created a model. Let's create a device. Import torch so we can predict on whatever device we want to use. Set up device. So device equals CUDA, if torch.CUDA is available, else CPU. And we'll send that to device, and then we will go model.load state dict, and we will pass in torch.load the file path to the model, which will be, get the model path, might just put this under here. Oh, the file path can just be equals args dot model path, torch.load file path. Now, is that the correct way to load? Let's just look up torch load. Load state dict. Yeah, that's it. Okay. Well, it should be. We'll find out in a second, sorry. So do you see what we're doing here? We're setting up a model instance, and then we're loading in the saved state dictionary. Load in the saved model state dictionary from file. Might just zoom in here. Can you see that? Oh, that's probably too big. There we go. That's actually pretty good. Return the model. What's this saying? And I'm going to just put in a print statement here. Print f loading in model from file path. So we've got our image loading in, we've got our model loading in. I'm not sure if this will work, by the way. We're going to figure this out. File path. So the file path here is, by default, is going to be args.modelPath. And the image here is by default, we'll call this image path actually. Image path equals image path from up here. So we're going to load the model. Load the model. And we need to pre-process the image. We'll load it in first. Load in the image. So image equals torchvision.io.read image, and we will pass in as a string just to make sure the image path, and then we'll go type torch.float32, load in the image and turn it into torch.float32, same type as model. Pre-process the image to get it between 0 and 1. Now image equals image divided by 255. Now we need to resize and transform, or resize the image to be the same size as the model. So image equals torchvision.transforms, and then we're going to go .resize, size equals 64. We might just pass it through. We'll go transform equals that. Why do we need to do this? Well, because we need our image in the same size of image that our model was trained on. So 64. Torch Vision transforms. So we'll go image equals transform image. And then we'll get the logits. So we will go model.eval because we're going to predict on the image. Turn on inference mode for inference. And then we're going to put image to target device. Make sure everything's on the same device. So here we're going through the three different things, three big deep learning and PyTorch issues. or not issues really, but just things you have to be aware of. Same data type. So the data you're predicting on and the model you're using have to be of the same data type. They have to be pre-processed in the same way. And your image or your tensors, your data tensors have to be on the same shape and size as what your model is used to, 64, 64, otherwise we'll get shape mismatches. And then finally, our data has to be on the same target device as our model, otherwise it will error as well. So if we put the model to the device here, which we've set to be device agnostic code, this is just what we have to be aware of. So the three things: same data type, same shape, same device. We'll get the pred logits, and now get pred probs. So pred probs equals, we want pred logits, and we can call torch.softmax on these on the first dimension. And then we're going to get pred labels equals pred labels equals torch.argmax of the pred probs on dim1, or pred label, because it'll be a single image. Now we want the class names here, so we might just pass in, we could just set up the class names manually for now. Set up class names. We could pass these in as an argument, class names. We're going to go pizza, steak, sushi. Set up class names, and then we're going to go pred label class equals class names pred label, and then we're going to go print. Let's get it info here, pred class can be pred label class, pred prob will be pred prob dot max, and we'll get that to 3 decimal places. Okay, so a fair bit of code here, but this is good practice for writing a bunch of Python code. So we've got a parser here to get the image path. Let's just see, I've already set this up to use the arguments. So maybe we'll just try to run our script straight away. What errors do we get? Write file predict.py. Writing predict.py. Let's just pass it in an image path here. So image, and I want to get an image from the test data set. You could randomize this so it picks a random image. Just going to copy the path here. Let's see what happens if we run this. Predicting on data. Oh, I never called the function. So this is where if name equals main can come in. Equals, is it main? I always forget the syntax for that. Yeah, that's what we need. If name equals main, call predict on image. So what this means is that if you call predict.py as the main script, it's going to have the name equal to main, and it's going to run this function. So let's just see what it does. Output. Where do we get that? Oh, output shape. Run that, see what happens. Predict.py. Oh, what did we get wrong? Matrix shapes are incompatible. Okay. You know what we didn't do? We didn't expand the dims. On image dot unsqueeze dim equals 0. Make sure image has batch dimension. Shape, batch size, width, height, or height width. Hey, there we go. Okay. So the prediction is wrong. Predicting on, oh no, it is right. Steak image. Wonderful. Predicting on data, pizza steak from the test data set, loading in model from models 05 going modular, pred class steak. Beautiful. So let's try it on a different image. Let's try it on a sushi image. This is from the test data set, by the way. Now we have a function that's going to predict on our images. Beautiful. Oh, sushi. It got that one right. Wonderful. We'll try one more for good luck. Let's go from the pizza. We'll select a random image from the test data set. And we'll go copy path. And we'll go here. Do we get 3 from 3? Sushi. Damn it. Okay, that's all right. But do you see what we've done here? We've covered a whole bunch of code here, but now we've got a way to just save all of our functionality of both training a model and now predicting with that model to Python scripts. We wrote all of this code just now, and we've saved it to a file. We could clean it up a little bit, but that's okay, to predict.py. So we could just copy this or download this, and now we've got a Python script. I wonder if... Yeah, it's going to give me a warning because it's a program, but that's all right. But we could save these somewhere else and then use them later on. So if I go back to GitHub, we could put them in going modular, and we could put the Python script in here. Let's just really test this out, and we'll go runtime, restart runtime. I'm going to start this from fresh to see if it all still works. I'm going to set up a GPU here to make sure that I've got a GPU. Now let's just run all of this code and see what happens to make sure it works. So we get the data. Let's just watch our file paths grow. Yes, we create all of these extra Python scripts because we've got datasetup.py, we've got engine.py. It's going to save all of these functions. We've got modelbuilder.py, utils.py, now train.py, which we've updated with various arguments. That was one of the exercises. That was exercise 2. We covered that here. Exercise 2. Use Python's Argparse module. And then if we keep coming down, train.py, yes, we've got that. Then we created predict.py finally, and we leveraged another script, model builder. We passed it in an image path and a model path to a saved model. We could clean this up a bit more to not have to hard code the class names and whatnot. But we've got a function to load in the model. And we make sure that we set up the model with the same hyperparameters as our saved model. That could be something else that you could potentially not have to hard code every time. That could be an extension. And then predict on image, we've got a prediction function here to load the image, or load the model, sorry. Then it loads in the image and turns it into the same data type as the model. It pre-processes the image to get the pixel values between 0 and 1 because that's how our model was trained on. We resize the image to be in the same size as the image that our model was trained on. And then finally, we make sure that it has a single batch size because our model is expecting data with the dimension, batch size, height, width, color channels. Then we get the prediction probabilities, prediction labels, And we use if name equals main to make sure that we run our prediction function here. Because what this little piece of code here is going to do is go, hey, if you run this predict.py function or predict.py program as the first program that comes after Python, it's going to be the main program that you're running. So anything that comes after that will run. And then we pass it in a test image. And we have our test image. In this case, it's pizza. It doesn't get it right. It gets it as sushi. That's another extension to potentially improve our model so that it gets better results. But let's finish this stream off with one last test image. What do you reckon? Let's go sushi. I haven't eaten sushi in a while. We'll copy that. Copy path. Which number did we get? 175783. Let's view this image. Sushi, okay, that looks pretty much like sushi to me. Let's see what our model thinks. Predicting on steak. Okay, so our model's not too great, but that's all right. We're going to improve that in the next section, which is transfer learning. So if you're watching this, I hope you gave the exercises a go yourself. If you have any questions, you can of course leave it on the GitHub discussions tab for the PyTorch Deep Learning repo. But I'm now going to save all of this code to, this is example solutions for notebook number 5. This is all going to be in GitHub. So add solutions for 05 under my repo PyTorch Deep Learning. And then if you go extras/solutions, add solutions for add updated solutions for 05. Extras/solutions, there we go. We save that. I go back to the PyTorch Deep Learning repo. Then if we have a look at extras solutions, we've got that file here, and later on, you probably won't worry about this if you're watching it later, but there'll be this live coded video will be on YouTube. Otherwise, I will see you in the next section.